Hello, everybody. Unfortunately, we missed to record the first talk of yesterday, so we just do a re-recording of it because it was a very nice talk, and I thank Erik a lot for doing it. So to introduce him, Erik is a PhD candidate at the University of Oslo, working on glacier surge dynamics and elevation change during the 20th and 21st century. He also works closely with the University Center in Svalbard, and with them, he works on a multitude of glacier-related projects. And with this, I want to give the word to Erik.
Yeah, thank you, Frank. I would like to believe that you were so taken aback by this beautiful re-photography that there was this little oopsie. But that's completely fine. I work with historical photographs for my PhD, and they are beautiful to look at, but we can get more than that. We can get elevation change data from these. And I want to show some recent publications that have come out on using these data on a regional scale and what we can maybe use them for. So to outline this talk, I'll take you through my journey of how I started with historical photogrammetry. I'll show two examples of glacier reconstructions at single glaciers, and then kind of motivate why we need these regional scale projects. I'll show two challenges, but also, of course, opportunities of these regional scale reconstructions. I have two examples from Svalbard and Switzerland in the 1930s. Then the question is, of course, what do we need in order to do more of this? And finally, I'll end off on some ideas for how to use them. I just want to highlight that this, I won't get into the technicals in this talk. I'll keep it quite as a kind of overview, and perhaps in the next talk I'll go into further into the nitty-gritties. So I am Swedish, and in Sweden we have a few glaciers of considerable size. For example, Storglaciären. This is a glacier that most Scandinavians know of. It has been visited quite frequently during the last 150 years. And in 1910, a geography student, 25-year-old, went up and took about 50 terrestrial images of this glacier. These are of a fantastic resolution. They are glass plates, large format images. And my question was, can we use these to extract elevation data? Now, this would imply historical photogrammetry, which, as just a very overview introduction, is regular photogrammetry, but with some extra steps. That includes that the internal geometry has to be solved for, and there are often not that many images, and the images can be quite noisy. Another challenge was that we didn't know exactly where they were taken. We also didn't know with what camera it was taken. So here's an example of one of these stunning images from Storglaciären. The first challenge was actually finding them physically, but that turned out to be pretty easy because they were archived in my father's office. He's a professor in glaciology and I would say historian in glaciology at Stockholm University. So that was easy, but scanning took quite some time. Then I put them into my favorite photogrammetry software and failed spectacularly, I could say, because these pictures could not simply be aligned by just pressing a line, unfortunately. At least at the time, the feature matchers were not good enough to to align features like the ones that you can see on the right here, this little snow patch in 4 different images. It could be because of noise, it could be because of that the angles between are too big. But they are perceptible to the human eye. So after a few weeks of placing tie points and ground control points, I had 1 glacier reconstruction. Jumping to the results, comparing this to 2015 reveals approximately 28% of volume loss. You can see that in the bottom right corner with the fancy colors. I also used a very complex, over-the-top, unnecessary mass balance prediction model to see when this massive change happened, and it seems to be in the middle of the 1900s that it really went fast. I could use this 1910 reconstruction to constrain this estimate. So this made me interested in what kind of spatial patterns we can see. Like, what can we find from other places in the world? So I ordered some images from Svalbard of a small glacier of equal or comparable size, at least, to Storglaciären, called Aldegondabren, which is on the western coast of Svalbard. In 1910 and 1911, Gunnar Isaksen, an early explorer, walked around and took 17 terrestrial images, which are just beautiful. And these have a very similar resolution. They are also large frame glass plates, but scanning took a very long time. It literally had to be fetched from inside a mountain in order to scan. That's a long story. And yeah, these have very similar challenges, such as that we don't really know anything about them other than that we have the actual images. Here's an example of one image from Aldegondabren. I also used aerial images from in between to get what kind of happened in many time steps. So jumping to the results here quite quickly, I found a 79% volume loss, going from about 1,400 to something like 350 million cubic meters. And this is in a very comparable interval to this equivalent or this counterpart in Sweden. And as you can see, it's almost 3 times larger. So that was quite surprising. And I also found some other things, like what most of us know, that elevation change rates are accelerating or increasing over time. So just to summarize where we are, there are these massive differences when comparing one glacier to another in 2 different regions. And that's incredibly interesting, but of course, this is not representative of all of Sweden or all of Svalbard. Therefore, we need more data. So I took a job to get more data. I was employed at this project looking at about 22,000 terrestrial images that were taken between the world wars in the Swiss mountain range. Now that's obviously quite a larger number than the 17 and the 50 before. But luckily they were all scanned beforehand, and the metadata was incredible. Like the location, the orientation of the images, and the camera make and so on was known. So that makes it doable in a short time frame, at least. The major challenge was scale. It was not really the photogrammetry itself. On a single glacier reconstruction, you can do little manual tweaks here and there, but here everything had to be autonomous. And I should note that these were stereo pairs, whilst the others were individual photographs. So they are kind of different, but still similar to a degree. Yeah, some challenges were that this internal geometry had to be corrected, the results had to be co-registered, and then interpolation was a big challenge. So interpolation contributed to the biggest source of uncertainty. We got about 45% coverage, which is good considering the age of the data, but it needed interpolation, of course. So we figured out this nice hypsometric interpolation approach, and we put it in this repository called XDAM that is now free for everybody to use if you're interested. So looking across Switzerland, we found a 52% volume loss. But at individual regions, this varies quite a lot. So close to Grosser Aletsch glacier, it's close to 0.7 meters water equivalent per year of loss, whereas in the Valley Alps further south, it can be almost half. So that was interesting, and we found some correlations between different geometrical properties, but it certainly needs more research. But if you're interested in this, please read the paper and have your own opinion. About 6 months before our publication, there was another incredibly impressive paper by Emily Gaiman and others from the Norwegian Polar Institute. She used about 5,500 oblique aerial images from Svalbard from 1936 and 1938. And these images were all scanned, but the metadata is quite poor. It's known to a few hundred meters where the images were taken, but not better. And so she needed to spend this immense amount of time placing out ground control points and tie points, about 70,000 of them. And I cannot stress how much work that is. I'm truly impressed. But it paid off. This publication is in Nature, and we now have this beautiful elevation change map over Svalbard. We see a 15% volume loss in the last 80 years, but there are these massive spatial variations, so more in some places and less in another. They could also use some impressive statistics to predict that mass balance or mass loss rates may double in the coming century. So if we want more of these, well, so what do we need? Well, first, we obviously need the data. And there's a lot of data from different places. For example, the coast of Greenland and parts of Antarctica were covered in the 30s by Denmark and Norway and some other countries. In Scandinavia and the Andes and Jan Mayen, there are beautiful looking aerial images. We either need metadata about these images or just a lot of manual labor. But my point here is that it's almost always possible to use. Finally, we need people like, or nerds like Emily and I, to actually do this. There are some costs involved, especially regarding scanning. Scanning is the biggest effort of all of this, and it might take quite a while to do. Then development and computation is also a considerable time, but especially scanning. So some ideas, just brainstorming for what we can use this for. Well, obviously we can use it for elevation change. We know that, but what about more uses? So some ideas are that we could use it in assimilation to validate glacial evolution models. So if it hits our known geometries, then it's probably right. We could look further into the parameters of what drives these spatial variations. And yeah, something like, I don't know anything about this, but I got the question if this could contribute to a global energy budget, and I don't know, but now we can try to tackle these questions. Finally, I don't know if anybody has yet looked at changes happening outside of the glaciers, such as mass movements, permafrost change, and changes in forest extent and elevation. And with that, I want to thank you for your time, and I look forward to if you have any ideas.
So yeah, Eliza is a PhD student at Stanford University, and today she will be talking about investigating the basal thawing in Antarctica with ice sheet modeling and ice penetrating radar. And yeah, so she works in the radioglaciology lab with Dustin Schröder, and she in her research she combines ice sheet modeling, yeah, with ice penetrating radar analysis to investigate the vulnerability of Antarctica to basal thawing. And yeah, with this, I let Eliza talk.
Does that look good now?
Now your slides disappeared. They look good, but
Can you see them again?
no, you stopped sharing.
That's weird. Do this one more time.
Looks good.
Great. Thank you for the introduction. Yeah, so today I'm excited to talk to you about my work investigating basal thawing in Antarctica with ice sheet modeling and ice penetrating radar. And what I'm really interested in for my PhD research is really understanding kind of this connection between the basal thermal state and the dynamics of Antarctica, and trying to understand whether basal thawing could play a role in mass loss from the Antarctic ice sheet. So I'd like to start with what is the basal thermal state. Here on the left is in a long flow cross-section going from the ice flow interior on the left to the fast flowing ice sheet margin on the right. And if you now look at the temperature at the bed, it goes from cold frozen bed where the ice is moving very slowly to a thawed bed at the point where ice is sliding over the bed and has reached the pressure melting point. Similarly, if you look at the map on the right, you can see thawed bed outlet glaciers near the ice sheet margin interleaved by these ice ridges characterized by having frozen bed. Now I want us to move beyond these snapshots in time, and I want us to consider temporal changes in the basal thermal state. Here you can see this can be broken into two processes, basal thawing and refreezing. And while both processes can affect the behavior and evolution of ice sheets, here I want to focus on basal thawing. And I want us to consider, what if some patches of the bed are close to thawing? So basically, as you can see in yellow, what if some parts of the bed are currently frozen but could be thawable? And where across Antarctica might these regions exist, and how imminently could they thaw? So as you might be thinking, typically basal thermal state changes are thought to happen over very long, slow timescales. But here I want to consider if there could actually be effects over century timescales, since that is the length of time that is typically focused on in projections of future mass loss, like the IPCC reports and things like that. So there is a body of recent theoretical work that suggests that a spontaneous onset of thawing could be possible. And basically this is this work looks at nearly thawed onset of ice streams where there could the internal ice thermofrictional feedbacks that kind of govern this onset of thawing. And I also think that the continued effects of climate change really warrant this investigation of thawing, where changes near, the ice sheet margin could affect the basal conditions of upstream grounded ice. So really here we are investigating if and how basal thawing could impact the century scale evolution of the Antarctic ice sheet mass balance, and whether basal thawing could affect sea level rise in this context. So for this investigation, I started with using ISSM and initialized the model with present day conditions across Antarctica to derive this map of basal temperatures that you see here. And then I used this model initialization as the starting point to set up 4 thawing experiments ranging from smaller to larger amounts of prescribed thawing, which you can see kind of in the schematic on the right. And then I run each experiment over 100 years after I've prescribed the thawing. Now, let me go into a little more depth in how I actually prescribe the thawing, and I'll give you an example, but feel free to check out my paper for more details on this experiment setup. What I do is in each drainage basin, which you can see one circled here as an example, I categorize the basal temperatures into thawed, thawable, and frozen based off of temperature thresholds for each experiment. And then I also know the friction coefficients for these regions from my model inversion. When I plot the friction coefficients for each temperature category as a cumulative density function, which you can see on the right, the curves are different for thawed, thawable, and frozen, where thawed has the lowest friction followed by thawable in the middle, and then frozen with the highest friction coefficient values, which makes sense when you think about the relationship that should exist between basal slipperiness and thermal state. So using the CDFs enables me to modify the friction coefficient in the experiments by reducing the friction in the thawable regions to match the friction coefficients in the nearby thawed regions. And so this is my way of capturing the effect of thawing in ISSM experiments. Now, once I run these thawing experiments over 100 years, what do I find? Well, here is my main result. And notice that everywhere the ice sheet response is mass loss, which I think is really interesting, but there is a lot of variability between drainage basins. So the plots show the 4 thawing experiments on the x-axis and then the rate of mass loss in gigatons on the y-axis. And you'll notice that there are 2 drainage basins with the highest mass loss, which are interestingly both in East Antarctica. And I think this result comes about because, East Antarctica in general is much colder, and much of the bed, is much colder than in parts of West Antarctica, where a lot of the bed is already thawed. And now I want to really look more closely at one of these basins, this bottom right one here, labeled DD prime, which is the George V Adelie Land region of Antarctica, and kind of take a deeper dive into what might be going on here and why does my model show such high mass loss. So this is kind of a combination of pieces in my model. There is a lot of thawable area in this drainage basin, and so that's one component. But this region is also really important because it contains the Wilkes subglacial basin, and you can see these ice streams that I labeled here are what drain the Wilkes basin along the George V coast here. And also, if we kind of, take a step back and look through some of the previous literature on this area, this one paper identified these critical ice plugs that are these patches of ice along the coast. You can see outlined in red here in the middle figure. And in that paper, they show that these ice plugs are sustaining the current configuration of the region. And they also show that if they're removed, which you can see by the red lines in the figure on the right, that this could basically, result in a lot of Wilkes Basin becoming vulnerable to retreat. So I think this leads to an interesting question, which is, what is the basal thermal state of the ice plugs? And could thawing be a way to potentially remove them? So at this point, we are at a place that observations, I think, becomes incredibly useful into this problem, because observations both provide a way to validate the larger scale modeling results and also further constrain the basal conditions. And we're incredibly lucky to actually have pretty extensive radar surveying in this region, which you can see in this map of radar flights flown over the last decade. And radar is useful for understanding the basal temperature because the attenuation rate is sensitive to the ice temperature, where you're going to have a higher attenuation rate in warmer ice. And also the bed reflectivity is sensitive to the subglacial environment, including thawed or frozen beds. So you're going to have a brighter reflection where the bed is thawed and there's water at the bed than somewhere where the bed is very cold. So then what I do is I'm actually able to, investigate the basal conditions using the radar attenuation and reflectivity to get out some constraints. So the first thing that I do is I process the radar data to back out the attenuation and reflectivity for all the flight lines that I have along the coast here. And then I also plot this spatially, which you can see attenuation rate, reflectivity, and ice thickness, and you can see the variation kind of along the margin where you have higher attenuation and higher reflectivity kind of dispersed between lower attenuation and lower reflectivity patterns. And then you can also see the ice thickness that I get out of the data. And what I do is I actually feed this into a logistic regression model. So the data that I put in is attenuation, reflectivity, and ice thickness. And then a logistic regression is useful because I kind of have these two categories, right? Frozen and thawed. And I want to know where some of these unknown areas lie within this range of between frozen and thawed. And so I train my logistic regression model on what I'm calling my known frozen and thawed areas, which you can see in this map below. And what I'm using to classify thawed and frozen here is obviously, ice shelves have thawed beds. We also know that really fast flowing glaciers have thawed beds. So I use a velocity mask basically just to find the parts of the bed that are really fast flowing. And then on the opposite end, I can kind of assume that the really, really slow flowing areas between these glaciers probably have a frozen bed. So I use this data to basically train my model. And then what I do, which is the very interesting result now, is I'm able to predict the thermal state in all the other unknown regions. So then I feed all of the data through my logistic regression model, and this is the results that I get. And so here you can see, along the coast, what this data set is kind of predicting in terms of where the bed is likely frozen or, more likely thawed according to the logistic regression model. I outlined the ice plugs in black here, and you can see that parts of the ice plugs kind of stand out as being in this intermediate near thawed range, which I think is an interesting result. And then obviously you can see some other areas like the ice shelves and some of the really fast flowing areas kind of, standing out as thawed, and then some other areas between some more of the fast flowing glaciers standing out as, areas where the bed seems frozen. So this work is kind of able then to be a next step in updating the model results and kind of providing more constraints on the thermal structure on a more localized drainage basin scale. So with that, I wanted to take you to some of the main takeaways from my work at this point. We started with just asking the question, does basal thawing matter? And my model results show that the answer appears to be yes, that there is a relationship that's pretty strong in some basins where you have more thawing produces more ice mass loss. Some of the unknowns still that came out of that work, though, is what physical processes can actually lead to basal thawing in the first place, and under what conditions and under what timescales can thawed bed actually be sustained. And if you're curious more about that, I'll point you to my paper that came out on that recently, and you can read more about that if you'd like. And then I think the other kind of big piece of this work is how interesting the George V Adelia Land region is. It does seem to be somewhere that could be really important to understand and better constrain the thermal conditions here, because there could be large sections of the bed near the ice sheet margin where it could be vulnerable to thawing. And I think that kind of leads to a pretty provocative question of, could basal thawing affect the stability of Wilkes subglacial basin? And that is ongoing work that I'm currently writing into a publication. So I think I'll leave it with that. And if you will be at AGU next week, I will be there, and feel free to talk to me more then, as well as asking questions at the end.
Thank you, Eliza, for another very interesting talk. Yeah, so let's directly move on to the next speaker before we come to the discussion. And this is Andrea Securo, and he is from University Foscari of Venice, and also from the Institute of Polar Science of the National Research Council. And yeah, he just started studying Greenland local glaciers through remote sampling and geomatics at University of Venice. But today he will be talking about ice caves in the cryosphere and climate in the Julian Alps. And then, yeah, this is from his work he just finished as his fellowship, as research fellowship in the National Research Council, if I got it correct. And yeah, with this, welcome, Andrea. Yeah, Andrea.
Okay, thank you, Falk. Can you hear me well?
Yes, it's good.
All right, perfect. So thank you for the introduction. And today I would like to talk about the work we are currently doing on ice caves in the Julian Alps, especially with a focus on what we are doing to monitor in the underground cryosphere of the area. But I will also do a little bit of brief introduction about the cryosphere of the Julian Alps and about some small glacial bodies of the area. So the Julian Alps are in the southeastern European Alps at the border between Italy and Slovenia. It's a pretty small area of less than 2,000 square kilometers that is characterized by the presence of limestones, and especially with the combined presence of glacial and karstic form, making it the glacial karst landscape. It's widespread in several areas. The highest peaks are the Triglav in Slovenia and the Montasio in Italy. But what is peculiar of the area is that this is the area with the mean annual precipitation that is highest in the entire European Alps, with values that are reaching 3,300 millimeters per year in the Canine Massif, which is one of our core studies areas for the caves. And that is very interesting because leads, of course, to a lot of snow. We are talking about 6.8 meters per year of total accumulation, but we have a lot of years that are exceeding 10 meters of complexity depth of snow. So it's a very snowy area for the Alps. The glacial bodies of the area are all very small, but they are well studied and monitored. In particular, there are 2 of them that are currently monitored here on a yearly basis, doing a mass balance and stuff like that. There is the lowermost Italian glacier, that is the one you can see above up there, the Montasio Occidentale. And then there's also the Canine East that has some gravitational movement, but like very slow, so it's more of a nice patch. What is interesting of this area in particular, despite they are small bodies, we had a volume of 2.35 square kilometers during the Little Ice Age maximum, and a huge reduction now till 2006, leading to 0.35 square kilometer of total area. But from 2006 till nowadays, we observed a positive anomaly, so a slightly increase in the elevation of these bodies. So this is very interesting compared to the rest of the Alps, what's happening to the rest of the Alps. So today I will focus a little bit more on ice caves. The region is well monitored and studied thanks to some work started by Renato Colucci and also by the very advanced speleological cadastre available in the region. The region you can see here is Friuli Venezia Giulia, which is in the northeast part of Italy. And here you are seeing a map of more than 1,000 cryo caves where you have snow and ice inside in the area. As you can see, there's this high elevation plateau area here on the right, that is the Canine Massif, that has more than 60% of the ice caves of the entire region. And so it's a perfect area for starting the studies and the monitoring of ice in caves. Sorry, I forgot to say that usually caves are at an altitude of more than 1,000 meters, the caves with ice inside. And with the mean winter air temperature below -2 degrees and with the mean annual air temperature below 2 degrees Celsius. So when I talk about ice in caves, I mean, I'm talking about permanent ice deposits in caves. So the, ice that is at least 2 years old inside caves. As you can see, these caves from these photos we took in 2014 and 2022 are losing a lot of ice. And so we are losing a lot of potential paleoclimatic information in the area. In a lot of places, ice in caves is found in areas where we didn't find ice outside the caves. So it's still an important matter. What was the problem was that all the mass balances inside caves were based on discrete measurements, so punctual measurements with a meter or something like that. So we tried to, using the available technology, to improve these kind of monitorings. So as the first talk talked about structure from motion, we are also doing that at a completely different scale inside caves to detect the 3D change detection. Recently, we also started using LiDAR. And then we are adding ground penetrating radar for estimating also the volumes of ice in caves. So these are the 2 caves where all the studies of the area started, and they are very different one to another. The first one is the Vasto Ice Cave. Here we have a big glacier, let's say, compared to the rest of the cave, that brings inside a lot of snow. And here the main ice accumulation mechanism is fernification through a cycle of melting and freezing. So we have a lot of inputs from outside. Instead, in the other cave, the Leupa Ice Cave, despite sharing the same elevation, here no snow is going inside, and all the ice forms through the percoloration from the ceiling to the refreezing at the surface of the cave. Also, the air circulation is different between the 2 caves. We have the creation of a cold air sac in Vasto Ice Cave, while Leupa Ice Cave has a way more complex cave air dynamics with the air that is flowing also below the debris, and that created an air-filled cavity that you can see in the first photo up there, but completely disappeared nowadays. So with a melting from above and below. Briefly, I'll talk about the workflow without going too much into details. The workflow is made to be very fast in the acquisition, then processing takes way more time. So it says a phase of data acquisition, data processing, and cloud comparisons. So the data acquisition starts with the ground control points. So it's a local referencing phase, not an absolute one. We try to use very light instruments like the Disto-X, an instrument used for surveying caves, used by a lot of cavers. And we just start surveying some ground control points placed along the area. Then there is the photo acquisition. Here in caves, you cannot respect the traditional geometry of structure from motion like outside. but it still works. You just have to have a very big overlap, and also you have to pay attention to the lighting. That is fundamental, of course, in caves. Then we have the acquisition of ground penetrating radar, nothing special here, just a small scale. So we can make a grid. We use 250 to 500 megahertz antennas, but nothing special like the traditional use of ground penetrating radar. So then the processing starts with the structure from motion. As you know, this technique is widespread nowadays in geosciences. So we start from 2D photos and we semi-automatically, let's say, derive a 3D point cloud through the matching of different clusters of pixels. So we start with the first output, that is this sparse cloud. It's a cloud of points that has no spatial reference, and that is why we are introducing the measurements coming from the ground control points here. We can also we also use sometimes the total station, but we notice that of course the total station is way more precise, but it takes too much time, especially in caves. It's a little bit dangerous, let's say. Then we can reprocess the cloud that is then densified through the multi-view stereo, so algorithms coming from the computer visions. And now we have tens of millions, or even we reached 1 billion points for one site. So we have a very high resolution that can then be processed once again to obtain a 3D model like this one that is textured and has a sub-centimeter resolution in some areas. In some areas you can see holes, especially up in the rock walls, because it's not very easy. Here you can see on the left a comparison between the 3D model and a photo, just to prove that it's very high resolution, and also some ground control points in the area. And here I have a short animation that I hope goes well, because it's a little bit heavy, of the inside of the Leupa ice cave. That is this cave. You can see the ground control points, and there are some holes in some areas, but it's pretty good results being in caves using artificial lighting. This is one of the main chimneys of the area. All right, so then we go to the third phase, that is the comparison. Of course, every cloud needs a little bit of treatment, so noise reduction, cleaning, and stuff like that. But we used a very powerful software that is open source, that is Cloud Compare. I'm sure many of you heard of it. And also the alignment and the comparison is performed in Cloud Compare. The alignment is do manually, unfortunately. We had to pick some. Of course, the scaling has already been done, but the alignment needs some fine adjustment. So for that, we use the rock walls and the features around the cave. Then we use the multi-scale model-to-model cloud comparison algorithm, N3C2, which is very powerful and works also in full in 3D. That is way better than, for example, the difference of DM that wouldn't work in a cave like Leupa that I just showed you in the video. So it's very powerful also because it includes an accuracy estimation that is automatically detected using the resolution of the cloud and the alignment, accuracy, and some other factors. Then there is the ground penetrating radar phase. I will not go into the processing, but it's a traditional processing. But what is very nice with the ground penetrating radar is then we can obtain a grid with points, and we can integrate that in Cloud Compare software. So we can also make the volume calculation inside Cloud Compare in the same environment, and also make a lot of visualization mapping and stuff like that. So it's very powerful. And here you can see an example of the results. It's the monitoring of the Vasto ice cave, the first one where the snow is coming inside. You can see in red surface losses. It's like a kind of a mass balance, but of course we didn't convert it in water equivalent. You can see that because of the snow entering in the cave, you don't always have a reduction in volume. You have also positive years like 2020, 2021 that had an incredible year for the winter precipitation that is all blue, but then of course the year after there was a huge loss. This is another example in Leupa. This time you can see just 1 year of comparison, and in Leupa no snow is coming inside, and the volume variations are like constant. And this is a work done by Julian, where we have the variations. The first 9 years from 2011 to 2020 are made just with 1 point, but we see that there are no increases like we saw in the Basal ice cave. And also we can calculate the volume loss from the ground penetrating radar to the structure from motion data. So using the structure from motion as a ceiling. And we found out that 13.6 of the estimated total volume of the Vasto went lost from 2012 to 2020, while in the Alps ice cave, almost 50% of the estimated volume was lost from 2012 to 2020. So summing up, the methodology for long-term monitoring is based on structure from motion for surveying, but you can also use LIDAR successfully. Then is strongly based on M3C2 algorithm in Cloud Compare for the change detection and also potentially the mass balance. And of course, the ground penetrating radar, once is processed, is completely usable in the same workflow. What we found out is that firnification plays a major role in helping, let's say, the resilience of caves, of ice in caves. So caves that have snow and ice, snow inputs from outside, like Vasto Ice Cave, are way more resilient than the rest of the caves of the area. And this is, just for concluding, I would like to mention some other works that study the evolution of the glacial bodies of the area, and also of some glaciocast features, so dolines and shafts that have permanent ice and snow deposits inside, like the one we see on the top left. So these bodies have been monitored from 2006 till 2018 and also nowadays, and we found out that the positive anomaly that is found in the outer cryosphere bodies is also found in these snow and ice deposits inside dolines and shafts. So this is very significant if you look at the variations. I know we are talking about small ice bodies that have their local amplifications, but it's still a remarkable and interesting feature because we have plus 2.28 meters from 2006 to 2018 in the Julian Alps area, while we have minus 14.21 for the European Alps. Of course, bigger glaciers, but yeah, the difference is remarkable. Well, the snow and ice deposits inside these glaciocast features had an increase, as you can see from below, of about 1.2 meters on average. So still a positive from 2006 to 2018. So if you want more information about these studies about the Julian Alps, these glacial bodies and ice caves, I have put some papers here that maybe you can read, and I would also like to thank Renato and Costanza for the help. And that's it. Thank you. Here are some photos of the caves of the area.
Thank you, Andrea. This was another very nice talk with really nice images and impressive videos. And yeah, so I would ask if there are any questions in the audience to any of those speakers today. Yes, Roger?
Yep, thanks very much. Thanks to all the speakers. Enjoyed all three of those. First one actually is to Erik. Where you were doing your work in Switzerland, presumably there's quite a long, hopefully there's quite a long record of things like water levels in lakes and so on. Did you look at perhaps comparing the water losses estimated from the volume losses estimated from the glaciers to anything like lake levels to see where it went and so on?
Yeah, thank you, Roger. I have not. That was an interesting idea. One thing that sprung to my mind was the one massive problem that I had regarding lakes, which was dams that had been built between the 1930s and today, which I needed to. I eventually found a polygon that kind of masked them out, so I could remove it because it induced a lot of positive change. But that might. So do you mean by looking at at different lake levels and just? Wait, sorry. Could you elaborate?
I was just thinking if you got estimates of volume losses from the glaciers, it'd be interesting to think about where it all went. And the easy thought I had was lakes, but obviously there are other possibilities. Whether it's just fed straight down into rivers, disappeared, whatever. and really extrapolating the whole idea to things like, you know, places like the Andes and the Himalaya, where the glaciers are a seriously important water supply.
Yeah, that's a very interesting direction. In Switzerland, this image archive actually consists of around 50 something thousand images, and so we only picked the ones that covered or that directly looked at glaciers. So anything that is covered by that should be in the dataset, and there are orthomosaics and DEMs, so it should be possible to delineate lakes from the past. So that's certainly an interesting thing to look at.
Cool. Well, thanks a lot for all the grunt work that went into it as well. It looks like you've got an awful lot of potential student volunteer projects there. if you want to lasso them for it. Thank you.
Oh, thank you.
Okay. Zach, yeah, do you have a question?
Those are all very interesting talks. Thank you to all. I also have a question for Erik regarding the photographs that was stored physically in a mountain. What was that about?
Yeah, so I recently learned this. I was on a study visit to the Norwegian Polar Institute that houses, or they kind of own the images which are archived by the National Library of Norway, and I learned that they are inside of a mountain in a climate-controlled, dried out place that is supposed to last for like ever. And so the process of scanning the images means physically going into this mountain, to this it's an old mining cave and or a mine shaft, and taking them out, declimatizing them, whatever that meant, I didn't really understand, and then scanning them and then getting them back in the mountain. It made me a bit, it humbled my weight for these images.
Cool, thank you very much.
Okay, Ian, you have a question?
Oh, hi. Thank you, everyone, for 3 very interesting talks. My question is for Andrea. Can you repeat what are the thresholds in temperature and altitudes between the caves with ice and the caves without? Can you work out 50% thresholds?
There are more caves with the snow inside.
Mm-hmm.
There is also a paper that is well studied, all the relationship between the caves with snow and cave with ice, the area, that goes into details of all the stats and the altitude, from Renato Colucci. You can find it in the last slide, if you go back, was mentioned in one of them. And but there are way more caves with snow and ice inside than caves with just ice. But sometimes they are very site dependent, because there are a lot of microclimatic variations and inversions at the entrance. So we can find the ice caves at low altitudes, then caves with snow and ice at higher altitudes. It's all a little bit messed up. I mean, there are a lot of cases.
A very broad range of thresholds. Yeah, yes. Yeah. Thank you very much indeed.
Thank you.
Okay, are there any other questions? Roger, you have another one?
Yes, thanks. I'd like to ask Eliza a question, actually, and again, thank you for that talk. Presumably that was fairly low frequency radar that you were using, given it was all airborne, I think, from what I saw on your slide. I just wonder what it meant for the kind of vertical resolution that you were getting at the bed, and how reliable the bed reflectivities you found were. Were they very erratic and or very stable spatially? And I ask really because I always worry about things like tuned reflectors, where you've got a relatively thin layer compared to the wavelength of the radar, and you get interfering reflections from the top and bottom, and they absolutely confound the amplitude of the return you get.
Yeah, for sure. That that definitely can be an issue in some scenarios, and depending on the applications that you're using. With this this type of radar reflectivity analysis is a pretty standard thing that like has been done with these data sets for Antarctica, and has been shown to have pretty high accuracy of like the reflectivity patterns. But it's definitely something you have to be aware of, like in how you process the data, and check kind of those steps as you go through the processing, to basically make sure that you avoid kind of that stuff. Yeah, and all the plots I was showing was relative reflectivity, so I was looking at like the total, the changes in reflectivity relative to the mean, and when you plot histograms of that, like the total range of values matches with other papers and kind of like other analysis of what that range and reflectivity value should be.
Yeah, that's cool, because I imagine certainly in a daily land you haven't really got any control points from boreholes or seismic or anything like that, much as I'm sure you would like it. But
yes, that is correct. I would love if there was more.
Well, there's a Christmas break coming up. Sure, you can find something to do. Smashing. Thanks once again. Thanks to all three of you.
Okay, are there any other questions? Otherwise, I would have another question to Eliza, because similarly to the reflectivity, I was wondering how do you deal with like sloping layers and bumpy layers? Do you need to specially consider them?
So I'm not specifically tracing layers. When I calculate attenuation,
well, I mean bedrock with layers, sorry.
Say it one more time. You mean with bed?
The bedrock of like sloping
roughness?
bedrock, actually, not layers. Yeah.
Okay. Yeah. So I mean, basically, what I'm doing with my analysis is I pick the bed from the radar images, and then depending on the roughness and stuff like that, yes, there could be some error, but I use the bed picks to then calculate attenuation by basically decorrelating changes in attenuation with changes in ice thickness. So over a region where the bed is changing in thickness very rapidly, then you basically will need to look in a smaller like fitting range around your point to calculate attenuation, whereas really smooth areas, you're going to have to like look at a larger area to be able to come up with attenuation rates for that. And then from my attenuation, then I calculate the reflectivity values. And so the attenuation and reflectivity and ice thickness are coming out of my data from that method, if that answers your question.
Okay. Yeah, I think I need to work it out, but yeah, I think it does. Thank you.
Thanks.
Any other questions? Okay. Yeah, Erik.
I have a very short question also for Eliza. I'm also incredibly interested in the different GPR processing that you're doing, or is it GPR if it's airborne? Yeah, because I work a lot of with radar myself on Svalbard. And are these tools that you're using, are these developed in-house, or what? How do you? Can I have them?
Yeah, so this is kind of taking a step beyond one of a previous paper that was published in our lab, which I could put the link in the chat, that combines basically multiple different airborne ice penetrating radar surveys for Thwaites Glacier, and then calculates reflectivity and attenuation. And then this is kind of taking it a step further, doing like a 2D adaptive attenuation fitting method, and combining even more data sets. And obviously mine is looking at the Wilkes Basin area. And so that other paper has kind of like set some of the the first steps in this approach, but when this paper is out, then I plan to also, publish the code associated with this and kind of like the more detailed methodology of, how I go through these processing steps. So it's great to hear your interest and more motivation for, making my code clear and making it accessible for other people. So thanks.
Yeah, looking forward to it. Thank you.
Okay, I think we're getting close to the end, but maybe I would also have one more question to Andrea. And this is about what time span of climate records are we actually talking in the caves? Like how old is the oldest ice, and what would be lost if we just let it melt, or how valuable is it? Should we really go there and get some records before they're gone?
Yeah, there are some dating works that we're currently doing, but they're not published yet. We're talking in a lot of caves, we're talking about little ice age ice, more or less. And instead, we have some other caves in the area that have bigger ice volumes. I didn't show them today, and they have older ice, but still, of course, in the Holocene as all the caves worldwide. But I don't have precise dating available from them. Most of them are little ice age ice.
Okay, thank you. Okay, and then if there are no other questions, I would close this seminar. But before I want to first, is the question coming? No. Before I want to first, thank all speakers for 3 very nice talks we had today, and excuse for the difficulties we had in between. And then announce the next seminar, which is on January 11th by Jason Briner from University of Buffalo. And he will talk about the response of Greenland ice sheet to the past Arctic warmth, generating field data of ice sheet modeling. And then a last remark is that I am also currently searching for speakers for the next early career scientist talks, which are on February 8th and March 22nd. So if you are an early career scientist yourself and would like to give a talk, or have members in your research groups who you think would be interested, please let them know and get in contact with me or Tavi. And yeah, that's it. Thank you all for listening. And again, thank you a lot for these nice talks today.
Indeed, thank you to everyone. And we should say Happy Christmas, I think, and have a good time at AGU if you're going there. And see you in
that's
January.
true. Have a good transition to the next year.
Thank you. Merry Christmas.
Merry Christmas, everybody.